All right, so the goal for today is to talk about the mathematics behind streaming video. So if you've seen some calculus, it's going to be a little bit easier to understand some of the approximations that are going later. So one of the big issues people have with streaming video is we hate buffering. It's very frustrating to have to wait for the computer to reload and to get the image. But this is not the only possible problem in streaming video. There's a couple of other key issues. One of the most important is error detection and error correction. You're getting some message. You want to make sure you are correctly receiving the message. The other one, which may not be an issue if you're very trusting, is authentication. And so we're not going to have time to talk about it today, but how do you know the message is coming from the intended or the claimed sender? Somebody could be trying to send a virus or malware or something to put on your computer. So the idea of the need to authenticate a message is a huge part of the subject. I am going to concentrate today on just the issues of error detection, error correction, compression, efficiency. These are going to be the big issues, and we'll leave authentication for later. As a mathematician, I hate speaking in English. I would much rather speak in numbers. And really, there's not that much of a loss. So we can create a table to speak in numbers. And actually, I'm going to speak in a very specific language, binary. So this is zeros and ones. So imagine we have strings of length 5. There are 2 to the 5th equals 32 possibilities. So what I can do is 0, 0, 0, 0, 0 corresponds to 1. I'm sorry, to the letter A. 0, 0, 0, 0, 1 corresponds to B. There are no 2's in binary, so really 1 plus 1 is now 10. 0, 0, 0, 1, 0. This is C. 0, 0, 0, 1, 1. This is D. So if you're counting in binary, it looks like this: 1, 10, 11. I'm going to stop there. But this is how you would count in binary. Okay? I can represent 32 possible numbers. And so I have 32 pieces of information I can transmit. So I can transmit all 26 letters of the alphabet. But when you consider that I also have the digits 0 through 9, I have punctuation marks and whatnot, 32 numbers is not quite enough. And so then there are some very interesting questions as to what can you do to save the keyboard, to get those extra bits. Well, one of the things you could do is, rather than having strings of length 5, you could have strings of length 6. Well, the problem with strings of length 6 or length 7, you can transmit more things now, but now it's more expensive. When I was an undergraduate, I went to Morse College at Yale University. I love Morse. He's famous for 2 reasons: as a painter and as an inventor. And he was honored with stamps for both. It's very unusual to have 2 such disparate fields. When he created Morse code, a huge issue for him was efficiency of transmission. So if you look at how long it takes to type out the different characters in Morse code, the letters you use more frequently are faster to type. They're faster to transmit. And that was huge. So over here, if I go up to 7 or 8, I really don't use some of the special symbols on the keyboard that often. So I'm looking right now, the at sign you kind of use a lot. The squiggle sign I don't use that many times. Because of financial reasons, I don't use the colon. I usually use the semicolon. It's cheaper. How many of these special symbols do you really use? If you don't use them that often, to have all of the costs being borne equally is unreasonable. What you could do is you could save a special symbol, maybe the all ones, which then says whatever immediately follows is one of the next set of special symbols. And then by doing something like that, most of the letters can then be transmitted with just 5 things. And then the few expensive things you have a little thing that says capitalize what follows, use the special symbol. And so again, something like that is very, very useful. So the first issue is we've now agreed we don't have to transmit letters, we can just transmit numbers. Maybe we'll transmit 0s and 1s, maybe we'll transmit letters, ones, 0s through 9s, whatever. How can I tell if I've made an error in my transmission? I want to detect errors. So detecting errors. There are 2 very good methods. The first is the tell me 2 times. And just to make it a little bit more readable, I will use letters, even though it's painful to me as a mathematician, and I will write, oops. All right. So can you tell what word I wrote? Hello. I've got to speak faster because of the fire alarm. I could also do it like this. Hello, hello. All right? Which method is better? There's advantages and disadvantages for each. So one of the big issues is always, what metric do you use to compare things? The advantage of this method is as soon as I've gone halfway through, I know what the intended message was. The message was hello. With this one, I don't know what the message is until I get to the very end. The advantage of this one is as soon as a mistake is made, I know. For this one, I have to wait till the very end. Okay? Now, this only detects errors. If you get the message, what word did I intend? Was it cat or was it hat? It's not clear. If you had received this word, okay, almost surely then in this case I meant to send the word cat. I'm probably not sending you the word zat. So sometimes you can correct an error just because of common sense. But in general, if you have something like this, there is a danger of not knowing which is the word that was intended. So error correction is a huge subject. Right now, this is just error detection, that we've made a mistake. For a lot of things, it's actually enough to know when an error has been made. I am not even going to try to hide what company this symbol represents. I think in 21st century America, we've all been indoctrinated enough with ads that we all know that this is the company Target. Right? So what's the connection between UPC symbols and Target? I think they're working on fruit to be genetically engineered to actually have the UPC symbol appear on them, just to save time. No, probably not. But UPC symbols are almost everywhere, right? It's one of the greatest advances in 20th century. It's one of the greatest inventions, the UPC symbol and the barcode scanner. And the barcode scanner does two wonderful things. Not only does it tell the store how much to charge you, but it updates inventory in real time. This is one of the reasons why stores like Walmart became so good, is inventory management. In the old days, people's jobs were to go through stores and keep track of what products are on the shelves, what products are in the warehouses, and then manage the requests for resupply. With something like this now, it's all done automatically. Now, more than that, however, is done automatically. There are some things that are going on that you may not know. How many of you have a special promotional card for Stop and Shop, Worst Buy, Target, any of these stores where you scan your card and it will update your purchasing and it will give you the better price on the products? All right, lots of you have cards like this. They're collecting a lot of information about you. They like to correlate your purchases. There's a wonderful story of a Minnesota father who stormed into Target one day because he had just received coupons for pregnancy items. His wife was well past childbearing age. He had a very young son. He had a daughter in high school. There's no reason he should be getting stuff like this. And the manager for Target was very apologetic. He doesn't know how it happened. He will make sure it doesn't happen again. We'll send you the proper coupons. Let me make this up to you. And which a lot of people wouldn't have done, like a good manager. He called the guy back a few days later to just make sure everything was okay and to see if there's anything else they can do. And there's this pause on the other end of the phone. Well, I'm sorry, I couldn't hear you. Well, it turns out there was some extracurricular activity going on that the father was not aware of, and the pregnancy coupons were appropriate for his daughter. Target knew that he was going to be a grandfather before he did. How did Target know this? Through tracking purchases of people, data mining. It's one of the big fields of 21st century. All of this information is available. So when these things are scanned, they don't necessarily care who you are as an individual. They just care what are you buying together so that they can sell things more efficiently. What I like about the story is most people do not like to be thought of as a target. They don't like to be thought of as just a number. You like to feel special. You don't want to be singled out. You don't want to feel like Big Brother is spying on you and Target is giving you these pregnancy coupons. But at the same time, Target wants to give this person the pregnancy coupons. They want this person to go to the store. Why? If you have a little kid and someday you will have this wonderful experience, you don't want to have to go to 4 or 5 different stores. You want one-stop shopping. So if they can get you to go for diapers, maybe you'll also buy clothing, maybe you'll buy groceries and do everything there. So what Target did is more than just data mining. They did something very clever from a marketing perspective. They put on useless coupons, or probably useless coupons. Here's a coupon for a new lawnmower. And so they would make sure that the person would get the pregnancy coupons, but they would throw in a bunch of other random coupons for products so it would not look like you're being singled out or that you're being mined. And so that was a really clever idea by Target, so that now they could make sure that people got the ads that they wanted, the coupons that they wanted, without feeling like Target knew intimate personal details about them. Okay, so there's more that you can do than just the tell me 2 times. And one of the things is related to what UPC symbols does. It's called the check digit method. And we need a little bit of math prerequisites before we do this. So we need to do something which is called modular or clock arithmetic. So modular or clock arithmetic. So if it's 10 o'clock now, well, it's actually low. If it's 10 o'clock now, in 5 hours, what time will it be? 3. So 10 plus 5 equals 3. Okay, we know 10 plus 5 does not equal 3, but it does on a clock. So to make this mathematically precise, we write mod 12, and we put 3 lines, so like a triple equal. And so we read this as 10 plus 5 is congruent to 3 modulo 12. So x congruent to y mod 12 means 12 divides x minus y. So in particular, we get 3, 15. We could add another 12 and get 27. We could subtract 12 and get minus 9. These are all equivalent to 3 mod 12. Okay? We could actually use this to create a really nice check digit method, which the UPC barcodes use. So let's say I give you a string, 543782. What I'm going to put here is my check digit. What I'm going to do is I'm going to add and look mod 10, i.e. remainder when we divide by 10. So 10, 20, this is 29, so we get 29, which is the same as 9 mod 10. Okay? So what I'm going to do is I'm going to put the check digit here of 9. And so if my check digit does not match the sum of these digits mod 10, I know an error was made. So the question is, what's the advantage of this method versus the previous method of tell me 2 times? So we want to compare this versus tell me 2 times. As with most things in life, there's no such thing as a free lunch. There are trade-offs. The tell me 2 times, the advantage of that is you know where the error is. Here, I don't know where the error is. I only know an error was made. Also, some errors are not detectable. If I switch the 5 and the 4, I won't detect that. I will still get the same check digit. There's more improved methods that will actually allow you to detect when digits are switched. But there's a huge advantage that this has over tell me 2 times. So even though tell me 2 times can pinpoint where the error is, what percent of tell me 2 times of your message is actually the information you want to transmit? Only 1/2. Only 50% of message is the desired info. So what this means is half of your message is just checking stuff. Over here, with the UPC code, with the check digit, most of my thing can actually be information, and I just have a small little check at the end. If you've ever been to a supermarket and you have an item and it doesn't scan, the cashier does not hang their head down in embarrassment and immediately resign. They just scan it again. It's very cheap and easy to scan multiple times. So here, it doesn't really matter if you haven't read it. Quickly do it again. And so the check digit method is actually very nice and very powerful. Okay, but that said, we want to do more than just detect when an error has been made. We want to correct it. And so this brings us to Hamming, one of the most important characters in our story of the search for finding a method to not only detect but correct errors. Because this is being recorded and people under 18 may eventually hear some of these lectures, I will not use the actual language Hamming used. But Hamming was the low man on the totem pole, and as such, he had only access to the computers on the weekend. And so when he had access to the computers, this is how they used to do computers. They had punch cards, and you would punch things out, and you would have the stack, and you would feed the stack into the computer, and it would run until it came to an error, and then it would stop. And so maybe what might happen is you get 16 lines into your code, then there's an error, and it stops. And then because Hammond could only do things on the weekend, he would have to wait another week before he could run it again. And then he would find out, okay, error now on line 26. And it got very frustrating, and you could imagine what he said. Roughly, if the blank machine can detect an error was made, why can't the blank machine fix the error that was made? And so his frustration led to his creating Hammond codes and very efficient ways of not only detecting but correcting errors. So the first is to modify tell me 2 times to 3 times. So now we would send or hello, hello, hello. And you can argue as to, which is better to do. I think I would prefer this for many purposes, although if errors are really rare, something like this would be pretty good. And the idea is majority rules. If you ever have a situation where all 3 agree, wonderful. If all 3 agree, you probably haven't made a mistake. And again, you should be thinking that the probability of making an error is rare. We're sending 0s and 1s typically. If you have a 50% chance of making an error, then you're actually sending no information. Because then, if I send a 1 and I have a 50% chance of making an error, it's got a 50% chance of being a 1, 50% chance of being 0. Typically, the probability of making an error is small. So small that most of the digits are going to be correct. And so here, if I have 3 things right, okay, almost surely I got the right thing. If 2 out of 3 are right, it's very unlikely that both things were wrong the same way. And so if 2 out of 3 things are right, I will go with majority rules. So if you've ever seen the movie Minority Report, the story is much better than the Tom Cruise movie. That's exactly what was going on there. They had these psychics, and if 2 out of the 3 psychics said you were going to commit the crime, you were going to commit the crime in the eyes of the law. Now, if I give you something like this, now we're pretty sure that this is the word cat. So the tell me 3 times is really good. It can correct 1 error out of every 3. But there's a huge disadvantage. What percent of our message is information? Only a third. So only 33 1/3% of the message is information. So this is quite bad. Most of our time we're actually spending on checking information and not actually sending the actual text. So what I want to do is show you another method called the square method. And it works as follows. So this is D1, D2, D3, D4. So this is the message we want to send. So we want to send the string D1, D2, D3, D4, all 0s and 1s. So we're sending 0s and 1s. And now what we're going to do is I'm going to extend this as follows. And over here, I'm going to send D1 plus D2 mod 2, D1 plus D3 plus D4 mod 2, D1 plus D3 mod 2, and D2 plus D4 mod 2. And so now you see the giant square. I actually don't need the entry down there. So for example, if I want to send the message 1101, so here's my message. And now what I have to do is say, okay, 1 plus 1 is 2. So what is 2 mod 2? What's the remainder of 2 when I divide by 2? That's just 0. 0 plus 1 is 1. What's the remainder of 1 when I divide by 2? It's just 1. So this is also 1. 1 plus 1 is 0 mod 2. So this is the message I would send. So imagine we receive the following. So 1, 1, 0, 0. So I'm going to put this in red because I'm going to let you know here's where I made the error. So I'm assuming I'm only going to make 1 error in the transmission. And let's just say for specificity, the error was made in the middle. The same argument works for all the other places for the error. Now what's annoying is you could have the error in the check digit, which you don't care about. So unfortunately the error might actually be in the check digit. But let's say we make one error, and for definiteness, let's say it's here. So 1 plus 1 is equal to 0 mod 2. There can't be any errors in this line, because if there was only one error, this equation would not work. So all three numbers here are right, or I've made two errors in this line. And we're assuming that there's only one error that's made. If I look at this line, 0 plus 0 is 1 mod 2. That's wrong. There's a mistake here. I don't know which one of these is wrong, but I know one of these three is wrong. So let me circle this row. Something is wrong in this row. Let me look at the columns. 1 plus 0 is 1 mod 2. Yes, 1 has a remainder of 1 when I divide by 2. This is all correct. 1 plus 0, no, that's not 0 mod 2. There's a mistake in this column. So now I know there's a mistake in the second row, there's a mistake in the second column. There's only one element in both. And not surprisingly, it's the number we've circled in red. So this method allows you to detect and correct one error. So can detect and correct one error in 8 digits. And how much of our message is actually information we care about? 50%. And 50% of the message is info. Over here, we only had 33% of the message being information. So in terms of download time, this is significantly better. 50% of the message is what you want. But there is an advantage of tell me 3 times over the square method. And it's not that it has a better name. The advantage is this detects and corrects one error every 3 digits. This detects and corrects one error in every 8 digits. So again, the more frequently you're going to make errors, the more advantageous the tell me 3 times will be. For the most part, however, if errors are really rare, this is much better. I would much rather have 50% of my message being information than just 33%. There are other advantages as well to these searches. So this is the Hamming 7-4 code. If you look very closely, the numbers in digits 3, 5, 6, and 7 are in bold. The digits in 1, 2, and 4 are not in bold. So 1, 2, and 4 are the first 3 terms of a very famous sequence. I will give you the next term in the sequence. 1, 2, 4, 8. Next term, 16, 32, 64. The way these Hamming codes work is you put check digits at basically the powers of 2, and the non-powers of 2 are your message. It turns out if you look at all numbers of length 7 that are 0s and 1s, one of 2 things will happen. So think of your favorite or least favorite or third favorite number that's all 0s and 1s, 7 digits long. It will either be one of these numbers, or it will differ from one of these numbers in exactly 1 digit. And it will differ from only one of these numbers in exactly 1 digit. So somebody give me a string of 0s and 1s quickly, because we don't have much time. 0, 1, 0, 1, 0, 1, 0. Oh, 1? All right. So is this on my list? So if we look, it's 1 away from this one over here. Or is that right? Oh, no, I'm sorry. That one is 1, 0. This is 0, 1. All right, so let's look here and see, can we find something that differs from this in just 1 digit? Which one? Second on the bottom?
To the left of it.
Okay. So this is 0, 1, 0, 1, 0, 1, 0. So that differs from this one in exactly 1 spot. No matter what number you give me, it will differ in exactly 1 spot. An interesting question is, what's the most efficient way of checking that no matter which 7-digit number, there's 2 to the 7 or 128 of these to check, it's either one of these 16 or differs in at most 1 spot. This is the Hamming 7-4 code. And so in the Hamming 7-4, 4 digits of 7 are info. That's 4 sevenths, or approximately 58%. All right, psychologically this is huge. We've reached the point where more than half of our message is information we want to transmit. So for me, crossing that 50% barrier is enormous. This is clearly better than the square method. The square method could detect one and correct one error out of every 8. This can correct and detect one error out of every 7. So it clearly beats the square method, but if you compare this to the tell me 3 times, it's not so clear which one is better. More of your message is information here, but the cost is that, unfortunately, the tell me 3 times can correct errors 1 out of every 3 digits. This is only 1 out of every 7. So there are massive generalizations of Hamming codes. This is wonderful in terms of efficiency. All right, so again, this is all in the setup to streaming video. We want to be able to receive information. And so we want to transmit as little information as possible, and we want to make sure that when we receive it, we've correctly downloaded the right information. So the next question now is, how do I transmit things like pictures? So before I transmit a picture, let's try to transmit a function. So let's assume I want to send this parabola. If I know that it's a parabola, I could just say, hey, yo-yo, I'm transmitting y equals x squared. And if I send that, then it's very clear what's going on. Imagine I don't know that this is a parabola. How would you send information to represent this curve? What could you do? Point by point. So let's send lots of points. So I'm going to send 100 points in each interval of length 1. This should give you a really good sense of what the curve looks like. Right? I think at this point we all agree it's a parabola. We can see the parabola. This is overkill. It's very expensive to send this much information. So rather than sending 100 points per interval, what could we do? We could send fewer. And so the question is, how many points do we need to send and still be able to capture the essence of the curve? So again, I'm using a parabola as an example, but later I will give you a function that is probably less familiar. So this is what happens now if we're sampling it and just sending 10 points in each interval. And so now I only have 80 points rather than 800. If you look at this, you can still see the general shape, but if you notice there's something fascinating going on. I have bigger gaps at the extremes and not at the center. Well, what's going on? Well, if you look at the function over here, the function isn't changing that much. If you know calculus, the first derivative is 0 here, the first derivative is small and through here, the function isn't changing much. Over here, my function is changing rapidly. The first derivative is large. If I take points that are equally spaced on the x-axis and evaluate, they're not going to evaluate to being equally spaced. And I have a danger of missing things. What I want to do is I want to do dynamic sampling. I don't want to sample equally throughout the whole region. I don't need to sample too much over here. My function isn't changing that much. I do need to sample a lot more in through here where the function is changing rapidly. So here is a function that should be a little bit less familiar to you. I'm not even going to tell you what the function is. So in honor of the year, I will sample it 365 times from -3 to 3. And in the first method on the left, I'm sampling it uniformly on the x-axis. And in the second method, I tried to sample it uniformly on the curve itself. So what I tried to do is I tried to approximate the curve with a polygonal path. So instead of some curve like this, is just choosing a polygonal approximation so that each of these pieces was approximately the same. So I tried to calculate what's the length of the whole curve, chop it up into length over 365, move a polygonal amount to get to that. And if you look at it, which do you think gives you a better sense of what the plot should be? The one on the left or the one on the right? I'd say the one on the right. Look at all the data points we have in through here where the function isn't changing that much. The function is changing wildly over here. I have trouble sometimes just visually seeing with all these dots going on here, which way do things, where do I go as I'm drawing up? It's not clear. Over here, however, it's much clearer as to what's going on. And if you look, the places I'm having the greatest trouble is where my curve is changing the most rapidly. So the moral of the story is where things change rapidly, that's where you want to sample more. If you've ever watched an old Disney movie, what can you say about the background? The background in old Disney movies, very plain, but more than just plain, it's very static. The backgrounds in old Disney movies, it's expensive to animate. They basically just had a fixed background, and then they had characters with just small changes on that. And so, where do you want to concentrate your things? So now what I want to do is I want to talk a little bit about Taylor series. So if I give you a function, a Taylor series is a way to approximate a function as a combination of simpler functions. So I'm trying to write my function in terms of a combination of 1x, x squared, x cubed, x to the fourth, x to the fifth powers of x. And if my function is nice, I can write it as a combination of these polynomials. So this is the sine function. And so again, if you know it's the sine function you want to transmit, then just transmit sine and say, hey, yo, it's a sine function. Later today, we will look at something where it's not quite clear what the function is. Here is a wonderful polynomial approximation to sine. And so this is a fifth order Taylor series. It goes up to x to the fifth. It has 6 terms because, like mathematicians, we start counting with x to the 0 or the constant term of 1. And just by sending these 6 numbers 0, 1, 0x squared, minus 1 6x cubed, 0, and then 1/20th for the x to the fifth, we have a pretty good approximation of the function. If I go a little bit further, if I do a 7th order Taylor series and approximate up to the x to the 7, you really only start to see a difference close to pi. If I go even further, and the last coefficient is really small, 362,880, we can't even see the difference by I anymore. And so this is the power of polynomial approximations. Rather than sending all those points to get a sense of what my function looks like, I can just send these coefficients. Now what's going on here is the fact that computational power is becoming very prevalent and very cheap. If you have a phone, and I finally entered the 21st century, your phone can do a lot. It has really good processing powers. You don't have to send all the points. You can just send some coefficients like this, and then your computer on your end can take that and build up the function. So you don't have to send the entire image. You can just send a few key pieces of information, make sure those are sent correctly, because a mistake here now will propagate enormously, and then rebuild the function. So we're taking advantage of the fact that when you're watching streaming video, you're not watching it on tea leaves. You're watching it on a computer, on something with some serious computational power. Now Taylor series is approximating functions in terms of the polynomials 1, x, x squared, x cubed, and so on. It turns out that there are other generalizations. Instead of using a Taylor series, we can use what's called a Fourier series. We can use combinations of the functions 1, sine of x, cosine of x, sine of 2x, cosine 2x, sine 3x, cosine 3 of x. These Fourier series do a really good job. It turns out that there are things that are even better called wavelets. But for the sake of this lecture, let's stick to Fourier series. As a Bostonian, for the most part, I do not like New York City. I do not like the Yankees. But there is something I have to give New York City credit for. Manhattan has a beautiful grid system. I am from Boston. I love Boston, but it is not a fun place to drive around. If you're in Manhattan, you can just tell, well, how many blocks east-west do I need to go? How many blocks north-south do I need to go? And you have this wonderful grid. And what's really going on is you have these 2 perpendicular directions. We have the east-west direction, and we have the north-south direction. It turns out that there's a way to define the angle between functions. And the functions here are not perpendicular to each other. But it turns out that these functions, 1 sine x, cosine x, sine 2x, cosine 2x, etc., they're all mutually perpendicular. So you can regard these all as different directions. This is my east-west direction, my north-south direction, my up-down direction. I've run out of words. But you can regard these as generalizations. And because they're all perpendicular to each other, it turns out these do a much better job than Taylor series. The other thing is, if I want to use a Taylor series, these coefficients come from knowing calculus and from taking derivatives. I may not know my function well enough to take derivatives. You can write the coefficients for the Fourier series by just doing some integrals. And so as long as I can approximate my functions, I can approximate these integrals and get the coefficients. So this is a huge advantage of Fourier series over Taylor series. All right, so as promised, here is a function that should not look as familiar to you as the parabola. I did x squared plus 4/10 of cosine of x cubed minus 14 sine of x plus 2. All right, this should not look as familiar. If I try to do it with Fourier series, this is taking just n equals 4 terms. Good fit, bad fit, okay fit, what would you say? I'd say okay. It's not great. It's pretty good over here. It's off by a little bit. It goes up when that goes up, goes up when that goes up, goes down when that goes down. It's a little bit off into here. It's not horrible. It's not great. Here's now going up to 8 terms. So going all the way up to cosine 8x and sine 8x. And so here is my linear combination of sines and cosines up to cosine 8x and sine of 8x. And you can see this is a wonderfully accurate plot. If I did it a little bit further than n equals 8, I could get an even better fit. This is the power of Taylor series of sines and cosines. And I really want you to view these sines and cosines and Fourier series as a generalization of these Taylor polynomials. The idea is we're taking a complicated function and we're replacing it with something simpler. Okay? So now we're finally at the crux of the lecture. We're going to transmit an image. So I want to choose a random image. Okay, well, this is not necessarily a random image. This is the T-ball team that I am proudly the head coach of. So never fear that you can test my patience beyond my limits. All right? I have nobody who's even 5 years old. I have people who are under 4. We have fun. That's what matters. I want to transmit this image. The way images are saved is you basically have pixels. So what you do is, we can even use the Manhattan thing again, I chop things up and I store a vector in each square. And what I'm going to store is a triple RGB, the red, green, blue values. And so if I want to transmit an image, what I'm really going to do is I have basically 3 different things to transmit. So I have my red, and it's going to be a function of 2 variables. My green, it's a function of 2 variables. And my blue, it's a function of 2 variables. And for each one of these, I need to figure out, what's the value in each one of these. So maybe it'll be a number between 0 and 1, which will tell me my red intensity. Value of 0 or 1, my green intensity. Value between 0 and 1, my blue intensity. So I have 3 functions to transmit. And these are going to be functions of 2 variables. So the whole idea is, rather than using polynomials in terms of 1x and x squared, we can either use 1x, y, x squared, xy, y squared, or we could do 1 sine of x, cosine of x, and now things get more complicated, sine of y, cosine of y, sine of x, sine of y, dot, 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 dot. And so just as we can generalize these Taylor polynomials to be now combinations of x's and y's, we would now have combinations of sines and cosines. And so we could have like sine nx, sine my. We could have sine nx, cosine my, etc. And what we do is we take our picture, and instead of transmitting every pixel, what we do is we try to look at the 3 functions, the red function, the green function, the blue function. And we approximate those functions as expansions in sines and cosines or wavelets or something like that. And then we just transmit a few coefficients. And what we're doing is very similar to what we had over here. We just transmit a small amount of information, and then we use the fact that we have a powerful computer on our end to then piece it together. So this is a great way to see how a lot of math connects. Depending on what metric you use, different aspects will be more important than others. So you have to decide, how expensive is it to transmit? How frequently are you going to make errors? Depending on the answers to those problems, you'll choose different methods of transmission. It's very important to compress images. You don't want to send pixel by pixel, especially when, if you have like an old Disney movie with a background that's static, there's very little change going on. You want to do dynamic sampling. So I want to concentrate over here. That's really where the change is happening. So dynamic sampling is huge. You look for places where the derivatives are large, where the function is rapidly changing. You concentrate your efforts there. So you may not always do uniformly spaced pixelation. And then you have these red, green, blues. You can write any color as a combination of these intensities, and then you just transmit these 3 functions. So this is a brief introduction to streaming video. Well, technically, it's streaming picture. I don't know if you really want to see the streaming video of the T-ball league playing. So, all right, that ends today's class. Thank you so much for surviving the fire alarm and the lecture outside. I will try to write up semi-nicely, if I can find some time, the proof of sine of h over h, and then just scan that in.